Hi, welcome to ICLR's Friday Forum for September 16th, 2022. I'm your host, Dr. Keith Porter. I'm Chief Engineer at ICLR, the Institute for Catastrophic Loss Reduction. This is one in a monthly webinar series hosted by ICLR, Canada's leading source for disaster resilience knowledge. Each month, we present recently completed research related to ICLR's mission to make Canada more disaster resilient. This month was unusual for Friday Forum. We brought you two talks. Last week, we had a wonderful talk by Dr. Jen Beverly about wildfire pathways. So if you missed it, check out her slides and the video at iclr.org. Today, we're fortunate to have two of Canada's leading hail experts to tell us what we should take away from this year's record-breaking hail season in Western Alberta, based on fieldwork that ICLR was glad to support. Our speakers are Dr. Julian Brimelow and Professor Greg Kopp, both of Western University. Dr. Brimelow may be Canada's foremost hail meteorologist. He serves as Executive Director of Western University's Northern Hail Project. Professor Greg Kopp is the Impact WX Chair in Severe Storms Engineering in Western University's Department of Civil and Environmental Engineering. He conceived and leads the Northern Hail Project and Northern Tornado Project. Here's our agenda. Our webinar will last 90 minutes. In a moment, our speakers will present for about half that time. Then I'll moderate Q&A for the rest of the time. Please feel free to chat your questions into the Q&A box at any time. I will, after the speakers conclude, I'll try to pose your questions in the order they appear in the Q&A box. If we have a lot of questions, I may only pose your first question, then move on to others, then circle back to your additional questions. Our webinar today is recorded. ICLR will post our speakers' slides and a link to the video by Monday or so. So if you have colleagues who wanted to attend but couldn't, please let them know. Greg and Julian, thanks for speaking to us today. Over to you.
All right, thank you, Keith. It's a pleasure to be here as always, and we're also grateful for the financial support that ICLR provides for our research. Julian and I are tag teaming today, and we didn't want to have to change over sharing a screen. So Julian is going to control the slides, and so Julian, if you could go to the next slide, that would be great. All right, what we're going to briefly talk about today is what the Northern Hail Project actually is, why it's needed, what we're doing. And really, at the end of the day, what we're concerned with is addressing societal risk and losses caused by hailstorms. And so what we're doing in that direction. Keith, in his introduction, said recently completed work. So I'm going to say that's partially true for this presentation. We completed our first summer of field work, which Julian is going to do the bulk of the explanation of. But we're also going to talk about where we're going with this, because we currently have a 5-year plan for the research. And in that sense, we are just beginning. And this summer was our pilot year where we were trying to figure out how to do all of this work and working and engaging with partners who also support us in it. So we'll talk about both of those aspects today. Julian, next slide, please. So I just want to give some of the broader context for what we're doing. I've given talks to this group before on the Northern Tornadoes Project, where we're trying to identify every single tornado and downburst in the country, really trying to capture all the wind events in the country. The derecho this past spring also kept us very busy and was part of what we've been identifying. Next, please. So we've talked about Northern Tornadoes Project before. Our data is all open access. The aspirational goal of the Northern Tornadoes Project, and that aspirational goal also extends to the Hail Project, is really to capture all the data we can for every single tornado in the country. And so that's our goal. We've started also with this, also including social science data, so understanding how people are affected beyond what happens to the built environment and the natural environment. But that's again, an ongoing project that's helped to springboard the hail work. Next, please. So this is the Northern Tornadoes Project team, and I just want to show this because when we started this in 2017, it was Dave Sills and I and several of our students in the first year, Emilio and Aaron, and we hired Joanne, and then the team has grown rapidly since then over the past 5 years. And when Julian talks about the Northern Hail Project and the size of the team, you can see maybe the trajectory that we're on. But this is work that's done by a large group of individuals with quite an extensive number of partners. Next slide. So just again, the broader context of this, ICLR has partnered with us for over 20 years, going back to the Three Little Pigs project, where we've been trying to make houses more resilient to extreme wind. If you can push the button one more time, Julian. So after 20 years of work, we've have some really significant outcomes with this year with the release of the CSA S520, which is the first consensus standard in the world to design for tornadoes. And in the May Friday Forum where we talked about some of this work. So this is fitting together again, tornado resilience and wind resilience. And so you can see how that would fit with the Northern Tornadoes Project. Next slide. And if you can push the play button, well, the video can go while I'm talking. I think everyone's familiar also with the Windy Dome. This is a video from my colleague, Dr. Germa Bitz-Wamlak, also professor in our department, Civil Engineering at Western. And the group has presented on the wind loads on tornadoes there. So this work again has been ongoing since about 2009 when the Windy Dome was first funded. Next one, please. And then we have the Hail Project this year. And so just giving the landscape of what we've been trying to do over time. We have all of these projects going on that we're coordinating. And just to give you a sense of also where we're going. So we added the Tornadoes in Tornadoes Project 2017. We started the Hail Project this year. We're also continuing the growth of the severe storms research by implementing, we hope, a portable radar, mesonet, lightning mapping array in hail and tornado prone regions. And we have grant funding requests in for that, but we're hoping that this will be operational in 2 years in 2024. And so we're trying to bring together a whole set of tools to identify and classify severe weather events, develop climatologies for that, capture the data on the impacts, and bring that all together for various different uses. And so the model from the Three Little Pigs project, where we have outcomes with the building code, we definitely with the Tornadoes project and the Hail project also want similar kinds of outcomes of helping to make Canada more resilient. So that's the larger context of where we're at. And at this point, if Julian, you can hit the next slide, I'm going to pass over to my colleague, Julian, who's going to talk about the Northern Hail Project and all the work that we've been doing this summer. So Julian, over to you, please.
Hi, Greg. Thank you very much for that. And thanks, Keith, for inviting us to speak to everyone today about our exciting new research that we're doing. And I know some of you have already heard about the Northern Hail Project, but for those of you who haven't, I'll just speak briefly to what is the Northern Hail Project. Essentially, the Northern Hail Project, the main goals are advancing the meteorology, climatology, and impacts of hailstorms in Canada. And right now, there's a huge gap in our understanding of the hail climatology in Canada. And because of that, it means that we can't really develop reliable tools such as catastrophic models. We're also struggling to predict not only nowcasts, but predict hailstorms in advance. So what we've come up with is a plan, and you'll see this permit here, it's data-driven. So the bottom tier is collecting data, analyzing those data, and then those data feed into tools and modeling even, and catastrophic models, so the NWP modeling and catastrophic modeling. And then ultimately, the outcomes are going to be benefits to Canadians, municipalities, businesses, and other stakeholders through improved building codes and things like that. Now, this work is not being done in isolation. We're working with partners. Our main partner is the ICLR, and we've also got some partners in Canada, for example, WeatherLogics, and we're also working with University of Manitoba and the IBHS in the US and Instant Weather. And as Greg said, this year we had our first pilot year, our first pilot field program. And it's a very small team right now, right? It's me and my research meteorologist, Simon Eng. And then this year we had Francis, who was leading the field ops in Alberta. And he had a lot of responsibility. There was 2 students. There was Chris Rattray and Mark Gartner, who were great in the field. They did an awesome job. So did Francis. They were very busy. It was hard to know, what to expect going into this year, but I warned them they'd be guinea pigs, and they really were. And they were really good at, just biting the bullet and pushing through and working very hard. So why do we need the Northern Hail Project? Ultimately, it's about reducing impact. So we all saw the damage caused by the first billion-dollar hailstorm in Canada. Really, it was a miracle it hadn't happened sooner. And I am quite confident in saying it's not going to be the last billion-dollar hailstorm in Canada. And what we do know is that there are certain things that we can do to reduce the impacts or to deal with impacts in a better way post-storm. So we want to understand, how does hail inflict damage? It might sound like a simple question, but as I'll show you later, not all hailstones are created equally. And there are, exacerbating conditions such as strong winds that occur in tandem with the hail that can cause problems. So we need to look into that. And we also need to look into, well, what can we do about it? So there's several ways we're going to do this. We're going to look at impact receivers, building infrastructure, vehicles and such. That really hasn't been done in Canada. There has been some work done in Europe and in the US, but not so much here. We need to look at damage thresholds and, not just look at things that break, but also things that don't break. So if we can get a good inventory of reliable damage indicators and thresholds, then we can develop some codes to help guide, building and whatnot. And also we want to improve the climatology and meteorology. Canada's a really big country. It's a very data sparse country. And we don't have many upper air sounding sites. We don't have many surface stations because we're losing a lot of surface stations. So we need to find ways to better characterize the risk and impact of receivers or, buildings and infrastructure and urban centers to hail. And that requires improving our climatology. And lastly, we want to reduce damage. So to do that, we need to find out where the weak points are and how we can go about improving those weak points and taking mitigation actions to reduce the amount of damage. So I'm going to speak to some of that just now, but for now, it was an exciting summer. It was a very busy hail season over central Alberta, and we were really shocked and also very happy that we had an event on the 1st of August where we broke the record for the largest hailstone in Canada. The stone fell just northwest of Markerville in Alberta on the 1st of August. As you can see in these 2 pictures on the right-hand side, this area is no stranger to severe hail and bad hailstorms. This was a really bad hailstorm in the Markerville area back in 2006. No, this is not winter. This is 10th of August. And as you can see that day, there was a lot of hail. The siding on this little farmhouse has been shredded. The trees have been denuded. And on this day, it looks like the largest hail was golf ball, but there were really strong winds up to 100 kilometers an hour. And that wind-driven hail damage is really problematic. So before speaking to what happened on that day, I just want to give people a quick tutorial on what it takes for a hailstorm to form and what controls the size and amounts of hail. And this will also help us understand a little better when I speak to the impacts of climate change on hailstorms in Canada. So one usually looks at the larger scale processes that are present, the antecedent conditions on days when we have hailstorms. And the first thing you need is instability. If the atmosphere is not in stability, thunderstorms can't develop with strong updrafts. Then you also need moisture. That moisture essentially acts as fuel for the updrafts and the thunderstorms. And by moisture here, I mean low-level moisture, so low moisture in the boundary layer near the surface. And then one needs sufficient CAPE. It's not only enough to have some instability and some moisture, you need to have a lot of buoyant energy in the atmosphere, because that buoyant energy, to a large extent, governs how strong your updrafts are going to be. And it's not one-to-one, but typically the stronger your updrafts, the greater the likelihood there is of severe weather and hail in particular. But then we also need vertical wind shear or bulk wind difference. And the reason for that is, in order to grow hail, we need updrafts that ideally are larger in volume and last a long time. And wind shear is very critical in organizing these updrafts in a way that allows them to last sufficiently long to grow large hail. It can take up to an hour to grow a really large hailstone. So that requires the updraft to be of similar duration. And then you can have all those things and you can still have no thunderstorms. And that's because there may be a negatively buoyant layer, or capping lid we call it, or convective inhibition, SIN, in the low levels that prevents, it's like putting a lid on a pot of boiling water that prevents the storms from forming. So if you have low SIN, then you can get thunderstorms, and then you need a trigger. So a short wave coming through, a dry line along the foothills, or some feature that's going to help lift those parcels to their level of free convection when we can get a thunderstorm. And then you can get some hail. So you see there's a lot of parts that have to come into alignment for us to even have the chance of hail. Then we have the macro scale and micro scale processes. So these are processes that are going on inside the thunderstorm. So I mentioned the sufficient updraft. You also need liquid water, so condensate, so supercooled liquid water drops. So that's the primary growth mechanism for hail in thunderstorms. You need hail embryos. So those are the building blocks of hail in the storm. They're usually gravel particles or frozen droplets, a couple of millimeters across, and they are essentially the building blocks, but you need enough of them. If there's not a lot of them, you're going to get fewer hailstones. If you do have a lot of them, could have a lot of hail. And then the growth time. And the growth time is governed by a lot of factors. And in recent years, we're finding out that, storm relative winds and things like that are really important in governing how long the hailstones have available to grow within the thunderstorm. And I spoke to this earlier, you need a sufficiently large updraft. The bigger the updraft, the greater the residence time of the hail growing in the thunderstorm. I've just spoken about storm relative winds. If the storm relative winds are too strong, the hailstones get advected through the updraft very quickly, and that limits the amount of time they have available to them to grow. And then we can get hail. So, a lot of things are going on, but you'll be surprised that still, despite all these requirements, hail is a lot more frequent than one might think. And that's become apparent with social media. And also in this past summer, when we had the students out in the field, there are days when, it looked very marginal for hail. And then we get a message from them saying, yeah, we're getting small hail out of this thunderstorm. So this is all to say that a lot of these factors don't operate independently. There's a complex interplay between them. So in the future with climate change, how is this all going to play out with all these, factors operating together, sometimes in opposite directions, sometimes in the same direction. But what we're finding is that in the future, the amount of instability and moisture is expected to increase. The warmer the atmosphere, the more moisture it can hold. And that'll have a concurrent increase in CAPE, but also the convective inhibition may increase. So it could be that we have fewer but stronger storms in the future. Of course, the warmer the temperatures are, the higher the melting level. That means that there's more potential for melting, but we're finding that that's really only going to be expected to affect smaller hail, so non-severe hail, not so much large hail, and really not much of a factor for giant or even bigger hail. Changes in the vertical wind shear are unclear. There is indications there could be a decline, but other guidance is suggesting there isn't. But what is important is, when all these factors come together on a given day, whether it be now or in the future, that the odds are leaning towards there being bigger hail, especially if there's sufficient wind shear present. The one problem we do have now is with our modeling studies is predicting whether or not there are going to be more or fewer triggers in the future. And that's because we're operating at a relatively coarse resolution, and we don't have the ability to do really, fine scale modeling, although that is starting to happen in the literature, and we are seeing some results from that. So 1st of August, 2022. So the antecedent conditions on this day, when I first started looking at these maps, it's like, okay, this looks like a typical setup for a severe thunderstorm day over central and southern Alberta. Nothing here stands out as, oh, wow, that, things are going to go crazy. But once you start digging a little deeper, then I'll see in the coming slides, there were some signs that something really big was in the making. So we had an approaching upper air trough, and in conjunction with that, we had an upper air jet stream. It wasn't a particularly strong jet stream, about 65, maybe 70 knots at most, coming in across the Rockies from the southwest. This is the trough at 500 millibars with some, positive vorticity centers moving through across the Rockies. And then in the low levels, especially, we had, at least according to the models, a southeasterly flow. In reality, the winds were a bit more easterly to east-southeasterly rather than southeasterly, and that's actually quite important. But what they were showing and what we were seeing in observations is this red area, which is basically where you have a high theta E, equivalent potential temperature. Basically, that means you've got a lot of moist static energy, you've got a lot of energy in the boundary layer in the form of moisture and heat, and that's going to fuel the thunderstorms. So we also had strong lapse rates on that day. Temperatures were above normal, and there was abundant vertical wind shear. So we were expecting supercell thunderstorms, but however, the devil is always in the details. Okay, where were those storms going to form? When were they going to form? And then what areas were they going to affect? Were they going to be long-lived, or were they going to be relatively short-lived? And if you look at the sounding here, you can just see this purple line is the path followed by the parcel. So we've got a lot of buoyant energy, and we've also got really strong winds aloft. So, looking at this, any meteorologist will tell you this is a day when we're expecting really strong thunderstorms. So here's just an event overview of what happened that day. So as expected, there were severe thunderstorms. They developed in the late afternoon, and most of them developed deep in the foothills and then intensified as they moved to the east. The strongest of these storms, this is radar data you're looking at here. It's actually the mesh project, data from the MERMS product. And it started way deep in the mountains west of Rocky Mountain House, and it continued to move eastwards and intensify. And then around about just west of Markerville, you can see it starts to move to the southeast. And this is usually a sign that the storm is starting to spin up. There's non-hydrostatic pressure perturbation effects, and those cause the storm to dive to the right of the steering winds. And that's when things started getting really nasty. And then the storm continued to track eastwards. I mentioned crossed Highway 2 just north of Innisfail, and I'm sure you all saw the videos and the pictures in the media where there's some very frightening scenes for people on Highway 2 when the storm crossed the highway. Luckily, the storm missed Red Deer, and it missed some even the smaller towns, and otherwise things could have been a lot worse. So the record stone fell about 5:30 just northwest of Markerville. At least that's based on radar estimates. And the storm tops from the storm were something else. The storms were punching into the stratosphere, right through the tropopause, and radar-derived echo top heights were more than 16 kilometers at the storm's peak. So our team was out that day, of course, as they were on every day. We're expecting severe storms. And this black line here shows their track in the storm chase vehicle or intercept vehicle, and this is the radar mesh. So, radar, you can see where the hail fell, the record hailstones. The radar mesh product was not indicating particularly large hail. It was trying to into really large hail in the vicinity of Highway 2. I think some of these hails, it was predicting over 8 centimeter diameter hail here, but in the vicinity where we have the largest hail, it was only predicting about 5 centimeters at most. But the team first intercepted the storm when it was quite far to the west. They also deployed a probe, and I'll speak to that a bit later, sorry. They found 2 centimeter hail at this point. They collected a couple of bags of hailstones. We had a mobile freezer that was worth every dime we spent on it. It was incredible to have that in the car. It could keep down to minus 18. So they'd collect these hailstones in bags and then put them in the freezer in the car that was running up the car's battery. They then went a bit further to the east and they found a bit bigger hail, 4.1 centimeters, and they collected a sample there. And then they went a bit further east and got even bigger hail and collected a couple of bags. Then they went east for quite a ways and then dove south to cross the hail swath. And at this point, when they came across the really big hail. They found it under a copse of trees, which was probably helpful because they were there about 15 to 20 minutes after the hail fell, which is actually really good. That's what we're striving for this summer, but it's actually really hard to get to the location where the hail fell within 20 minutes of it falling. And a bit farther to the south, they found what turned out to be the largest hailstone. And there they collected 7 bags of hail. And then they continued on diving south of the storm track. And then east of Highway 2, they found more really large hail, and they collected 1 sample there. And then they continued on, and that mission went on into relatively late in the evening. So this is the hailstone that fell. It's a new record, obviously, just over 12.3 centimeters, beating the old record from Cedoux, Saskatchewan, coming in approximately 293 grams. The old record was 290 grams. And the bulk density here is about 0.848 grams per cubic centimeter, which is relatively low, but it's consistent with other hailstones that were scanned. This image that you saw rotating in the bottom right here is a 3D scan that we made with the help of our good friends and colleagues at IBHS in the United States, who flew all the way up here. It's their first international deployment, rapid response deployment to scan hail. So I'm sure some of you are asking, and I know I was asking, was giant hail expected on this day? And that's a difficult question to answer because it's really hard to predict extremes in advance, especially if you're talking a day or two. I mean, that's true for rainfall or precipitation, but it's particularly difficult for convection. So Environment Climate Change Canada, they issued these thunderstorm outlook maps, and they had identified this area of central Alberta for a threat of severe hail and strong winds and heavy rain. And they were predicting up to 5 centimeter hail in association with the strongest storms in that area. NHP for field operation logistics have also been issuing this past summer a day 2 outlook for hail just over our project area over south central Alberta. And you can see this yellow shaded areas where they were expecting a possibility of severe hail. And then this darker orange shaded areas where they were predicting likely severe hail, so an even bigger chance. Now, both Environment Climate Change Canada and our forecasters were maybe a bit too far to the north for the expectation of storms. Overlaid here, we have the radar of storms that developed on this day. And here's our, our culprit, the southernmost storm that passed just south of Red Deer that produced the record hailstone. So it was just on the edge of the envelope. But, you've got to keep in mind, this forecast here was done at full day in advance. And I don't think anybody was thinking, not that I saw or heard about, there being a potential for a new record hailstone on this day. But when you dig a little deeper into the data, you find that there were some signs that something ominous was afoot. The models on this day were too warm and too dry in the low levels. They were predicting dew points near about 15 degrees Celsius, whereas the observations on this day showed dew points approaching 20 degrees Celsius. So this would have meant that the updrafts would have been much stronger than expected. Sometimes we find it useful to look at intensity of thunderstorms and hail size in this what we call CAPE shear space. And on the bottom here, we have an indication of updraft strength as a function of your cape. And on the y-axis here, we have your vertical wind shear. Typically, the stronger the vertical wind shear and the stronger your cape, the more intense the storms are going to be and the greater potential for severe hail. And in fact, and you see that here, these circles, each one of these circles represent observation of hail size and the associated cape and vertical wind shear derived from proximity soundings. And we also adjusted the surface conditions to represent the air feeding into the updrafts. So if you were using the model data in this, you would have been over here, but actually, if you use the observations, you bring it way over to the right here. So, in the 7 to 10 centimeter range. So this is an indication that, yeah, we were definitely getting out there in terms of severe weather potential and extremely large hail. What we forecasters may not have known is that with the dew point approaching 20 degrees Celsius, if you look at the data for Red Deer Airport, which is about 20 kilometers east of where the hail fell, on the 1st of August, going back 40 years, your typical dew point is about 11.5 degrees Celsius on this day. And it can be as low as 2.5. And up here we have the 18.5, 19 degrees that was observed on that day. So had people known in advance that, wow, we're going to be looking at dew points that are the highest they've been in at least the last 40 years, that would have maybe set off some alarms. And in the States, they have this really neat diagram, which is based on weather balloon data or sounding data. They have it for all their upper air sites. But I can conceive that you could have something like this for all the major cities or locations and aerodromes across Canada, where you use reanalysis data. And that'll help place things in context, your cape or principal water or whatever parameter you're looking at. And I think that'll be really helpful for forecasters if we had a product like that. And what would also be helpful is we have real-time updates. So, for example, here we're running the WRF Hailcast model. This is from WMI. The model it's a 3-kilometer grid spacing model, and it was trying to show us long track severe hailstorm passing just north of Red Deer, sorry. That was only about 30 kilometers north of where the actual storm developed. And it was predicting a maximum hail size of 4.5 centimeters. But you got to keep in mind that this was based on data that had the moisture way too low. And I have no reservations in thinking that the hail would expected, in the forecast, had they used the actual conditions, would have been a lot larger. So we need something that allows us to integrate the latest observations into the surface fields and then any attendant metrics that are related to those surface fields. And then you could have rerun this again in near real time and, got an updated forecast. Oh, now we're looking at really big hail on this day. So how does human-caused climate change factor into this? And I asked that question, and then right below there, Kevin Tramperth contradicts that. And I really like the way he frames this. Kevin is an internationally renowned climate scientist who worked at NOAA. I think he's retired now. But the real answer is that nowadays, all weather events are unfolding or developing in a climate that has changed from what it used to be. So all events are affected by climate change because the environment in which they occur is now warmer and more moist than what it used to be. And we're seeing that with this, with the Calgary hailstorm, we saw it. It was more moist and warmer than normal for that time of the year. And again, we're seeing it here for the Markerville storm. We're also seeing this in observations and in modeling. So if you look on the right-hand side here, this is a paper we published a while ago now in Nature Climate Change, looking at the days of greater than 2 centimeter hail and a metric that we call the accumulated kinetic energy. Basically, it takes all the hail predictions for a given day and the kinetic energy associated with that hail size and integrates them over a summer. And then we looked at changes over the summer between the current climate and the future climate. And you can see that in our area of Hail Alley, there is expected to be an increase in the number of severe hail days in the future, and also an increase in accumulated kinetic energy. Also, to the point of changes in the future, We're seeing that several states in the US have broken records in recent years. I think 4 or 5 states have set new state records for hail in recent years. And Australia broke its national record twice in quick succession as well. And then we had the new record in Canada. But it's easy to, jump to the conclusion, well, this is, definitely suggesting something's going on. But there is a caveat here in that we are now seeking out large hail. There's a more determined effort in the States and in Australia and even in Europe and in Canada to identify these events. And, we have to be careful of jumping to conclusions, but urban expansion is also definitely playing a role. Exactly how big a role, we don't know yet, but we have to keep that in mind. So how is the Northern Hail Project addressing societal risks? I'm going to shift focus here a little bit. And we have intended outcomes. The one is the identification of failure modes. So how does hail inflict damage to buildings and infrastructure? A lot of work has been done in the US on shingles by IBHS, but now we need to start moving our focus to other forms on the building envelope, like siding, for example. We desperately need to improve climatology, and this is not going to be easy to do because we don't have surface data everywhere in Canada. We don't have radar coverage everywhere. So we're going to have to get creative, and I'll speak a bit more about that in a little bit here. But, it really needs to know where and when does damaging hail occur in Canada, and it might be in some places that might surprise us. People who live in those areas won't think anything of it because it's what they see year after year, but, for others, it might be a bit different. Linking climate and weather to impacts. How do we link antecedent atmospheric conditions to the resulting damage? So are there any indicators that, we're going to have strong outflow winds in association with the hail on a given day? Because the winds really do increase the impact energy of the hailstones. It also means that some surfaces that ordinarily would be protected by the roof are now exposed and subject to damage. And we need to develop risk reduction measures. So what steps can we take to reduce hail impacts? We can't move houses, but we can build better roofs. We can build better building envelopes. We can put our cars away in the garage, in advance of a hailstorm's coming, for example. So this is all going to be done ground up by collecting data. It's going to be really important that we get good ground truth data for which we can answer some of those questions that I just mentioned. So what we're going to be doing is looking at damage and impacts investigations, site surveys, in the field building performance. And we're also going to be using hail report and remote sensing monitoring to get national coverage. And that's going to include social and news media. We've got field operations, like I mentioned earlier. So we had our first pilot program this year for in situ hail collection. We can't do that everywhere in Canada, and we can't do it all the time. So we're going to have to also, again, get creative how we do our field operations moving forward. So as we expand the net. And we're also going to be using remote sensing and specialized observation platforms. We're going to be running our own radar soon, which will be in research mode. So we'll be able to, try out different algorithms and different techniques to identify hail using a variety of radar-derived parameters. We have satellite, and then we also have some specialized sensor networks that I'll talk about, for example, the Distrometer network that we're hoping to deploy in Calgary. So just to show you how effective it can be to have data, people on the ground collecting data. And like I said before, we've had this pilot season. It was a very ambitious and very successful pilot season. We did get lucky in that there were a lot of hailstorms. If we'd done this last year, it would have been a very different outcome because the area was in drought and there were very few hailstorms or even thunderstorms at all. We had a team of 3 in the field for 2.5 months, which was a long time. The primary goals for this were to test concepts, develop operating procedures, and collect high quality ground truth data. So the team sampled storms on 20 missions. They sampled 38 storms in total on those 20 missions, and they sampled the storms at 272 locations. So if you look at the map on the right here, these black lines show where they were driving around. If you zoom in around Red Deer where they were centered, it looks a little crazy because that was their starting point. But they went as far as the Saskatchewan border. The problem we face is that even though we have pretty good radar coverage in this area, the terrain is not very favorable, and neither are the roads. And that's something one definitely has to keep in mind when planning missions and identifying areas in the future. So if we were to have another field, say, team deployed in Saskatchewan, you'd have to choose an area where the roads are pretty good and where you have reliable radar coverage. And each one of these points is where the team sampled a hailstorm. At the end of the summer, we had 55 bags of hail. It's over 100 kilograms of hail. And those hailstones are now being safely stored at the Canadian Ice Core Lab in Edmonton. They were very kind and generous to allow us to use some of their world-class freezing facilities at the lab. And the plan is this winter is to analyze those hailstones. The team drove almost 20,000 kilometers to sample the storms and to maintain the hailpad network. So it's very labor intensive. You spend a lot of time and money on fuel, and it's not easy or cheap to do field studies like this, but the value in the data we get is worth its weight in gold. So we learned many valuable lessons and that we hope to rectify next year. And we also hope to expand the number of personnel in the field next summer. I briefly spoke to the hailpad network before. So you can't be everywhere always, right? So one way you can address that is to have a static network. So the network that we had is between Red Deer and Calgary. It's on a staggered grid. If you're looking close enough, that's so that the network acts like a net. So if the storm goes between two hailpad sites, the one to the east is likely to capture it. So that seemed to work quite well. So given the storms typically come from the west, and either have a westerly, southwesterly, or northwesterly trajectory, having the network aligned north-south like this, it makes sense. That we had the hailpad separated by about 3 kilometers in the north-south direction and about 5 kilometers west to east. There were 35 of them in total. During the summer, we had 93 hailpads hit by hail, and one location was hit by 3 hailstorms. A hailpad is 60 by 60 centimeters. We're using XPS foam that's 2 inches thick. And for such a small footprint to be hit 3 times in one summer is quite remarkable. We had excellent buy-in from farmers. We were a little apprehensive, how are they going to feel about people being on their land and setting up these hail pads. You can see one here on a fence post. And they were great. Some of them were very keen and actually collected hail or would notify us when there was hail in the vicinity of their hail pad. The team also tried some ideas about deploying hail pads ahead of storms. And I don't know which team member it was, but they came up with a great idea. Well, what happens if you attach an action camera on a little arm here to the hail pad? This is I think a $40 or $50 action camera in a polycarbonate waterproof casing. And I'll show you a video from that in a second. Maybe I'll just show you right now, actually. So this is sped up. This is near Rocky Mountain House, and you can see a really big hailstone falling on the hail pad there with some nice lobes on it. And you don't have any sound here, but you can actually hear the wind and the thunder, and it's quite really neat to watch. And there's another hailstone that's fallen on, and then one gets kicked off. So we're trying to establish how to best leverage these data. Similar videos we have of hail falling on the hail pad and it's raining. It's disappearing right before your eyes. And this is the problem we're facing, that if you don't get to the site soon enough, the hail's gone. So that's another attractive thing about the hail pad network, is that even if it's small hail, it's going to get recorded. The problem with hail pads is they're a lot of work, and analyzing the hail pads is subjective and it's very time consuming to do by hand. So one of the students who had programming skills developed some machine vision code using convolution neural network to identify different kinds of impact or indents made by the hail. And it's if you look at this 3D scan we made of a hail pad, you can see that it can be quite ambiguous in trying to identify these indents and correctly sizing them out. So if you can have code that does this automatically and objectively, that'd be great. The code even identifies if you have a hole here, for example, that was they call it foreign damage, but this is probably a bird pecking at the hail pad, for example. And it can also identify indents that were made by, possibly or most likely made by wind-driven hail. So we're pretty excited about this, and we're hoping that we can use this to analyze the remaining hail pads that we collected during the summer. So the one thing I want to speak to right at the end here is remote sensing of hail. I mentioned earlier, Canada's a big country. We have very few data points on the ground, so we're going to have to get creative. And we don't have radar coverage everywhere, obviously, and we have a limited ability to discriminate between hail size right now. But these are exciting times. We have the new dual polarization radar network, and I'm confident that we can develop some tools based on these ground data that'll help us improve the reliability and the skill of some of these radar-derived products to help provide better guidance where we do have radar coverage. We do have satellite, and there are some satellites that can identify hail, such as the GPM, and those data can be used, but their limitation is that they only identify hail aloft, and a lot can happen between say 6 kilometers above ground level and the surface. So they don't count for melting, for example. A very popular metric that we were using this summer, and that's being used widely, is the maximum expected hail size, or the mesh product. But it's very clear that this product needs further work and refining. And we have some ideas how we might be able to improve the mesh and make it more reliable. But to do all of this, we need ground truth data to improve the existing remote sensing algorithms and to develop new tools and to develop them to the point where we can confidently apply them nationwide and towards creating a national hail climatology. And to do this, I think we're going to have to leverage both conventional and dual polarization data for where we have radars. Another important tool that we can use that can be of a lot of help is deploying UAVs or drones. And now the price of drones is coming down. If you have a fixed wing drone, like pictured here, you can easily buy one that has a multispectral suite of sensors that can be to use a calculate a whole horde of variables such as NDVI. And you could even equip one of these with a thermal camera, because hail being cold, if you were to fly this over a hail swath, the thermal camera would be able to pick up, the width and of the hail swath, for example. So to do all of these things requires investment in time and people to collect a reliable ground truth data and collect information on hail damage to the infrastructure, and that's why we want to do more storm surveys. And also damage to crops using, like I said, UAVs. We didn't have enough personnel to do that this summer, but we certainly hope that we can do it in coming years. The other thing we want to look at is field operations hardness testing. We have a pretty neat video here of some large hail falling in someone's pool or pond in the backyard. It's important to remember that not all hailstones are created equal. Some are softer than others. Some are incredibly hard, and the other thing to remember is that hail is not a solid, it's kind of elastic. So you can deform it a bit before it actually breaks. And then another thing is a lot of the testing we've done to date has been done using perfect spheres. They're ice spheres maybe, but they don't have lobes. And I know IBHS is now starting to look at doing some tests where they hit shingles or siding with hailstones that are based on stones that actually fell. So they'll scan a real natural hailstone, they'll create a mold from that, and then they'll fire that at the siding or the shingles. And, we need to find out what dictates how and how much kinetic energy is imparted on these impact receivers. So this can be linked to conditions that produce the hail. Maybe some conditions in the environment produce harder hail, whereas other conditions produce softer hail. Our team noticed this past summer when, sometimes radar was indicating the possibility of large hail, but the team was finding large but pretty soft hail on the ground, whereas other times they're finding large but very hard hail. So why is that? And we also need to determine the importance of damage potential. how does hailstone shape and hardness affect its damage potential. This year, the team did a lot of effort to get a presence on social media and with the media, and also to engage them and solicit hail reports. And it was quite successful. There were some storms in Saskatchewan that caused a lot of damage, and we sent a survey team out there to look at the damage and get an idea of what the damage looked like on the ground. And as you can see, hail can be very destructive. I mean, if it gets big enough, knocking out the back window of a vehicle is no problem at all, or even just destroying siding on a house. And I've spoken to this before, but the one way we want to improve getting a climatology for Canada is to use remote sensing. Right now, this is, I think, the latest iteration of Atkins' map for hail in Canada. It was based on human observers reports, usually at aerodromes or airports. And that's very problematic because they're sometimes hundreds of kilometers apart. And obviously thunderstorms are on the order of a few kilometers to maybe tens of kilometers. So that's not really going to cut it. And the climatology right now doesn't differentiate between severe and non-severe hail. And like I just mentioned, uses observations from point locations, but hail swaths are localized and easily missed. And the conditions for producing non-severe hail versus severe, significant, and extreme hail are very different. So it's really important that we have a good tie-in between the observations that we use for the climatology and the antecedent conditions. And also to keep in mind, this is Gaspé in Quebec. I don't think many of us associate the Gaspé region in Quebec with hail. Maybe the locals do, but the community doesn't. But when you start looking at closely at hail and storms, like we were this summer, or like Simon was especially, we're finding that there's some pretty nasty looking hailstorms in parts of Quebec where we get very few hail reports from, very few. And using all these information, we hope to create a true severe hail climatology for Canada. We fully expect that the occurrence of hail and severe hail is going to be much larger than what we are predicting or reporting now. And it's going to be occurring in remote and unpopulated areas. And also perhaps ranges that are not typically considered hail prone. And I think one of the surprises might be areas in Quebec or even central BC, where I think there's a lot more hail than we think. So we really need to characterize these storms and their storm environments much more thoroughly. And at this point, I'm going to pass the baton back over to Greg, and he's going to speak to damage impact investigations.
Well, thanks, Julian. And so just quickly, as we wrap this up, we also, like with the tornado work, we want to be able to capture the impacts on society, on the built environment, on crops and agriculture, and all of that. So this summer afforded us a few opportunities to do detailed damage surveys. And again, the purpose of this is really to find out what is breaking, what isn't, material types and ages, how that affects it. Also to help us understand when things occurred, and really just learn what the impacts are on these storms. So next slide, Julian. So we had a few surveys this summer. As I said, we had three. We saw a lot of damage to siding in particular. We didn't see much damage to roofing. I'll talk about that in a minute. But we could see the differential impacts. And if you hit the button once, Julian, we can also see the effect of the wind on the impacts on the siding. So if there's not wind, obviously the hail will fall mostly straight down and will impact roofs. But when there's wind-driven hail, it does a few things. It increases the terminal speed of the hailstones as it hits the objects, hits the buildings and other things, and then can cause more damage and can get into the walls and windows and do damage there. And so that's one of the things that we also want to capture with this. When we talk about the climatology, it's not just the hailstones, and as Julian said, the hardness of them, but also what's happening simultaneously with wind. And so we want to develop the tools for that. And of course, this is an important factor for the losses and the impacts. We also saw vehicle damage, again, with some fairly large stones, but more subtle damage than the August 1st event Julian talked about earlier. And anyways, these were the kind of surveys that we saw this year. Next slide. And as Julian was mentioning, one of the things that we want to know, we can't always be there to pick up hailstones. We want to have tools to help better understand the radar impacts, and there's some subtlety with this that we're learning already. Some of the damaging hail, where the damage occurred in the upper left there, and the radar image with it, and then a differential impact in places where you might have thought there would be a damage. So again, developing the tools to connect the radar observations with the damage on the ground is one of the things that we're aspiring to do as we go forward in this. Next slide. And again, talking about roofs, obviously Calgary, there was a lot of roof damage there. The orange colors in that image on the upper right from the CRU adjusters was golf ball to grapefruit size hail in that area, and the damage caused by that was significant, as this audience knows. We're going to start using, as Julian mentioned, drones and other tools to do detailed damage surveys of these events, which we want to then correlate with ground observations of the hail and the meteorology to bring the whole circle together on what's actually happening in these events. Next one. Crops, of course, are a big deal, and we had an opportunity this summer also to look at crop damage. Here we have canola and corn. We want to be able to understand what's happening with those and be able to document what's happening with these as we go forward. They could be for us good damage indicators for what's occurring, but we have to understand how the hail is impacting them at different stages in their growth and with the effect of different crops. And also not shown here, things like forest and tree damage, and kind of bringing that all together to understand what happens with these as an indicator of the damage, and then connecting that back to radar tools to help us develop information about climatology and impacts. Next one. And satellite information. This is challenging for tornadoes. We use this as a tool as well to look for tornado damage, and over the course of the Northern Tornadoes Project, we've also seen hail damage in some of our analyses. It's complicated to understand the impacts of these. Certainly with tornadoes and what happens in crops and grasslands is very difficult to understand, and we have the same feeling of this with hail damage. So the satellite imagery can help us identify hail swaths, and we want to use that as a tool. Again, we need to do detailed damage investigations to understand what those mean on the ground for different crops. Satellite technology that's available to us as civilians is improving continuously. Bringing in infrared and using those as tools to identify using that to identify the crop damage and crop health after events is again something that we're endeavoring to develop with that. Again, this work can be very tedious, and connecting it to computer vision tools and machine learning is one of the things that we're doing. And this summer we actually managed to hire a couple of software engineers to the project, and getting them excited about meteorology and this kind of engineering of impacts of severe storms is exciting. But we do have, we're building that part of the team as well, so we're able to do this in a more advanced way as we go forward. Next slide. All right, well, just in terms, we're still analyzing data from this year. One of the things that we saw quite a lot of was damage to vinyl siding. It was quite striking to us. We saw very little roof damage, but we saw a lot of siding damage in the surveys that we did. We also saw window damage, and we saw breaches of the building envelope. which of course is always a concern because then you have water intrusion, which increases the losses quite significantly. We're also, as I mentioned, interested in non-structural damage indicators like trees and things like that. So again, trying to get a whole picture of what's happening in these events, and then connecting that with the actual hailstones on the ground when we can do that is a real way of developing much more information about the risk of these hailstorms. Next one, Julian. So to that end, we want to develop intensity scales. You can see from left to right on this image, minor siding damage to quite extensive damage and window damage. And so you can have this variation of losses. And what we want to do is connect that back to the intensity of the storm. So the hail and its characteristics, and also the wind that's driving it. So we can bring all of that together. Next one, Julian. And in Europe, they have something that's akin to the Fujita scale that we have for tornadoes. They actually have hail intensity scales. And so you can connect the damage observations, and here they do it to the hailstone size and the energy that the falling hail would have. So we're going to be using the data that we find here. We're going to be doing additional experiments. We're hoping to add even further instrumentation into the field so that we can actually measure the terminal speeds of hail in storms, and then relate that to those damage observations. Do experiments in the lab where we, like IBHS, throw and drop hailstones onto objects and connect all of those up so that we can develop a damage intensity scale that's particular for our conditions here in Canada and North America. So that's one of the things that we're going to be working on over the next 5 years with this project. So next slide. And I think it's back to you, Julian, for the summary in the last slide.
Thanks, Greg. So yeah, just to wrap things up here, preliminary summary of our pilot year. We did some identification of failure modes. We're already identifying materials particularly vulnerable to hail impacts. Greg spoke to vinyl siding. Vinyl siding was a big problem with the Calgary hailstorm, and we're seeing that again across the prairies. And there's knock-on effects. It's not just that your vinyl siding is getting destroyed. Like Greg mentioned, you could get, your building envelopes compromised, and that has other knock-on effects that drive up costs and impacts. We're starting to improve the climatology by building a detailed record of the location, timing of severe hail events across Canada. We leaned heavily on social media this year, and we'll be doing the same next year. But a lot of this is about reaching out, educating people, engaging people, getting people excited about reporting hail. And every data point is really valuable. And then we want to start linking climate and weather to impacts. So improving our understanding of the conditions leading to damaging hail. In the coming summers, we might be releasing some weather balloons in the field as well, should we get the funding. And that'll be very exciting to see how those environments evolve, and what the impacts of those evolving environments are on the thunderstorm or hailstorm and the actual hail falling out of that storm. And then we're ultimately going to be developing risk reduction measures. Like I said, we're already identifying materials performing well in severe conditions, and some that aren't performing so well. So this is going to be a learning process, and we started it, but we're still a long ways from the finish line. But it's an exciting time to be doing hail research. We have a lot more tools available to us now than we did 40 years ago when we had the last field program to look into hail in Canada. And with that, we'll just sign off. Thank you very much.
Gentlemen, thank you so much. That was a great talk. I learned a lot. We have 3 questions in our Q&A box, and if we don't get more, I've got plenty. Joan Clausen asks, what was the record high dew point at Deer Point, at Red Deer, prior to 2022? What was the dew point at Red Deer when the hail was observed in this same general area on August 1st, 2006?
Going back 40 years. I didn't have time to go back farther than that. But in the last 40 years, previously the highest dew point was approaching 17, 18 degrees. When those were days when there actually weren't any thunderstorms. On this day, the dew point was actually exceeded 20 degrees in some locations in the vicinity of the storm, in the area where the storm was feeding off. It was definitely the highest dew point in that particular area for this time of the year.
Sorry.
First of all.
And could you tell us amateurs what the dew point is and remind us why it matters?
Right. Why it matters, dew point's a measure of the amount of, it's a relative, you got to be careful with dew point. A more accurate way is to talk about the mixing ratio, but meteorologists often use the dew point. So that's the temperature you have to cool air to get condensation at the same pressure. So generally speaking, the higher the dew point, the more moist the air is. And the dew point can't exceed the dry bulb temperature or the air temperature. That's its upper limit, because then you have saturation. And it's important because the more moisture in feeding the updrafts, the more latent heat release you have, and that increases the parcel temperature and the buoyancy and the updraft strength.
Awesome, thanks. Scott Davis asks, he says, thanks for the presentation. Has there been research into the impact of hail and building resilience in climate change strategies, such as solar panels, indoor greenhouse farming, and such?
I don't know if Greg knows of anything. I do know that there has been some research on wind turbines, because hails are a problem for the leading edge of the wind turbines for abrasion, and also on the towers themselves. I'm not aware of anything on solar panels, but that is something that someone should be looking into, because yeah, I mean, it's an evolving landscape and we need to take that into consideration for sure.
Awesome. Joan, I'm going to come back to your second question, but first, Stuart Kober asks, I believe that Weather Modification Incorporated, WMI, is still employed by the Insurance Bureau of Canada to seed developing hailstorms in the Calgary to Red Deer region. You may be collecting samples that have been influenced by the seeding. Are you taking this into account in your analysis?
Do you want me to take that, Greg? Or?
Sure.
Yes, we are. In fact, one spin-off of the research that we're doing this year is that we're going to be doing a chemical analysis for silver in the hailstones. We already submitted our first sample to a federal lab in Burlington, and they processed that first sample for us. So moving forward, we will be doing that. And this will include hailstones collected within the WMI project area, and also hail collected outside the project area. But we're talking about very small numbers here in terms of the trace amounts of silver. And there's also danger of ground contamination. So you have to be careful about jumping to conclusions, and we're going to need a lot of data points. But yeah, that's very much something that we're cognizant of.
Cool, thanks. Our executive director, Paul Kovacs, says, Julian and Greg, great presentation, great initiative. Radar observations are used by Environment Canada to provide tornado warnings. Can radar observations be used to provide hail warnings? For example, warning to shelter vehicles before a storm arrives.
Oh, definitely. I mean, of course, Environment Climate Change Canada right now, they're the authoritative source of issuing warnings in Canada, and they do include warnings. I mean, for the Markerville case, I think they're warning of ping pong to golf ball size hail in association with that storm. What we're not doing right now is what they're doing in some other countries, where if a storm's approaching an urban area, some countries, the insurers will send a text message to their subscribers and warn them that the vehicles are under threat from a hailstorm entering the area, and that they should take put those vehicles away if they can. I think there's room for improvement there for sure.
Awesome, thanks. Scott Kaler asks, just looked up dew point record in Red Deer was 23.3 C on July 13th, 1953. Any comment?
There you No, I didn't have time to go very far back. When I looked back to the early 50s in using the ECMWF reanalysis for the Calgary hailstorm, there was a similar period in the early 50s where Calgary had similar environments to what we observed in 2020. But, days like that are very few. And I don't know what time of that was. This the 1st of August record, Scott, or was this a record period? Because things are starting to wind down a bit on the 1st of August as evapotranspiration decreases because the crops are maturing. So maybe that's a discussion I can have offline. But yeah, that doesn't surprise me.
An anonymous attendee says all-time record. Jan Chipi Shrestha, apologies, Gyan, says, great project. Can you please clarify the link between climate change and hailstone frequency and magnitude based on the available data?
I can take this one, Greg, if you want. We have looked at data for the Alberta Hail Project area, or South Central Alberta in particular. The observational data set that we have is not the greatest. It was never designed to be used to tease out climate change signals or attribution. So that said, having looked at those data going back to the late 70s, what we're finding is that there is in recent decades an increase in the number of severe hail days over South Central Alberta. But I'd put really big error bars on that because we don't have a data set that's being collected from a consistent source, the same source using the same methods over that time span. But ideally, that would be great. That would be something, that's what we're hoping, is that our project, the NHP, will create a baseline that can then be used moving forward to answer those kinds of questions.
Great, thanks. Circling back to Joan's second question, Joan Klassen asks, what was the hardness of the new 2022 record size hailstone, or whatever scale of hardness softness is measured? On whatever scale measured?
We don't know. We didn't do a compressive strength on that. And Ian Giamanco from IBHS tells me that you can't do that after the stones have been refrozen. It just affects the structural integrity of the stone. The shape and volume remains unaffected, but the recrystallization and whatnot can affect the strength of the stone. So that's something we'd have to do at the time in the field, apparently. And we just didn't have the equipment this year to do that. But that's probably something that we're going to be trying to do moving forward, because Ian Giamanco and his crews do that when they do storm intercepts for hailstorms in the US.
Cool. Paul Kovacs's second question for you, Julian, is please discuss further your views about the research about the impact of climate change on the frequency of large hail in Canada.
Right. Well, that's one slide I showed you. The one area in Canada where at least the model guidance, and again here, models are not perfect, right? There are limitations, but we did attempt to use the models that, for what it's worth, actually did a relatively good job at recreating or mimicking the current climate in our future projections. And that was showing, northern BC and parts of Alberta were expecting an increase in the size of hail and the number of severe and significant severe hail days moving forward. The signals elsewhere in Canada weren't that clear. Now, that's not to say that we're not going to be seeing any changes in those areas. It just means that these particular model runs, there wasn't a consistent signal across all the models. So those maps I was showing you was a aggregated approach. So we only, shaded an area if there was agreement across all three models. Some models were indicating increases, say, over Southern Ontario, Quebec, or Southern Manitoba, but that wasn't shown for all three models. So that's what we have the most robust signal right now. But we really need to do more work on higher resolution modeling under future climate scenarios. And we're working with John Hailstorm at University of Manitoba and his team and University of Saskatchewan on doing just that, but those results aren't quite ready yet.
Terrific, thanks. Cindy Seafried says, once we understand all these underlying factors, will we then be able to find solutions to impact or change those factors to reduce the hail, like they do seeding to address the size of hail?
I'll answer the first part, and then I think Greg will have a good idea on what we can do to mitigate in terms of standards and construction. I don't think even if we do understand all the processes completely, I don't think there's much we can do to change what reaches the ground ultimately, at least not on a very large scale, and certainly not for some particular storm environments. But that understanding of what's driving these storms and how the hail's behaving, understanding that better. I mean, you'd think that we know the full speed of hail very easily, right? It's Newtonian physics, but it's actually very complicated. And that's one of the things we're going to be looking at. And once we understand that better, then that could drive other improvements. And then, Greg will probably can speak to how that might affect how we look at building codes and whatnot.
Yeah, I think there's two aspects to that. I mean, if we can get warning systems to people, they can get their cars into garages or things, which would reduce the losses significantly to vehicles, right? So if we can do something active for that, but you can't do that for buildings. So the approach for that needs to be in building codes. And we don't have any standards for hail, I think, anywhere in the world, really. And so I think getting a better understanding of the damage impacts and then doing cost benefit analysis like Keith did recently with existing data, I think is the way forward. And just like we do for tornadoes now, we have the CSA, which is a voluntary standard, but it's pointing the way of what to do for tornado design. I would expect the process here would be very similar. We develop a standard for hail impact design and hail resilience, and then we work to get that into the building code where it makes sense to add that. And again, the climate change parts of this are important. Is the spatial distribution across the country changing? There's things like that happening, and understanding that will be important as well to bring all of that together.
And if, since you mentioned me, we may see a change there. There's a code change request for the Alberta building code that may require impact resistant asphalt shingle roofs, at least in part of Alberta. Let's see. Reza Ajafi asks on behalf of Paul Joe, I think, what was the size distribution of hail on August 1st, 2022?
Oh, that's a good question. Perhaps not surprisingly, hail tends to follow a gamma type distribution. I'm told by the field team that in the region where they're collecting those stones, incidentally, that might have not been the biggest stone that day. That one of the interns did have an even bigger stone, apparently, but it fell and he couldn't find it in their rush to get it back to the vehicle. But they were spaced several feet apart. But there was quite a lot of them. I mean, it wasn't like there were tens of meters apart. So there were a fair number of them. It seems like there were more when the storm crossed a highway to it in Innisfail. Some of those cars, you can see the indents or the dents are very close together, and windshields are completely decimated. So, but again, those stones weren't quite as big. Not to minimize the size of them, but they were still baseball-sized hailstones or bigger. But it does seem that when we have these really large hail events, you get a scattering of especially large hailstones, which is a godsend really, because the impact energy of one of those stones is enough to kill a person.
Thanks. Ola Osipo Osibanjo says, great work. Aside from available ground truth of hail observations, are you currently making future predictions of hailstones in Canada? And if yes, what approach are you looking at?
I think Greg might. I don't know. I'm not sure how to answer that.
I'm not sure how to answer that either. I think what we want to do is understand the current climatology as best we can, right? And that to me is the starting point. And all of this field work and research is what we're doing to get towards that. So yeah, that would be how I would answer that at this point.
Okay. Jim Rennick says, really interesting presentation. Thanks very much. Great project, and it's good to see research addressing the damage done to property by hail. Earlier work focused on the hailstorm and its impact on crops with little attention to property damage. An excellent start and good to hear. So mostly compliment rather than a question. But any response or comments?
Well, thanks. Thanks for that. I think what we're trying to do is capture everything. And obviously you can't capture all the data, but our aspirational goal at the end of the day is really to capture as much as we can. And we haven't talked about it here today. We're also trying to understand the impacts on people and families as the recovery happens in these events, and people with blue tarps on their roofs for years, that has an impact on their life. And we're trying to also understand that as well. So we're trying to capture all of those aspects.
Awesome. And Paul, before I get to your third question, I've got one. I'm told that vinyl siding becomes more brittle as it ages. Are you able to, have you been asking the age of the vinyl siding that you've seen damaged?
I'm not sure if Simon has. When he did those surveys, he gave me ages, so he must have talked to the homeowners and asked them. But I think that's the kind of question we need to ask. And there's differences in the products as well. Vinyl siding has lots of issues, has also issues with wind. And so I think there's a lot of work to be done on that. It's an inexpensive product, so changing that kind of thing does have cost implications. So again, getting a good understanding of the climatology and whether it's just easiest for us to cover the cost as it happens as a better option than mandating the difference is something that we need to discuss. But I think it's going to affect poorer families more than wealthier families. And so that's also something to consider.
Awesome. Paul Kovacs asks, both of you, the use of drones to examine damage would be an excellent expansion of the initiative. How can drones be used to examine the hazard? Presumably it'd be unsafe to fly into an active storm.
Drones are being used more and more. This past year, there was some amazing footage of drones in tornadoes that actually showed some failures of houses that were quite interesting to look at from my engineering perspective. We're not talking at this point about flying drones into the storms, but we would like to have drones available to fly immediately after. Again, the high wind environment makes it challenging to fly these things, and to get the kind of resolution we need, we fly pretty low. And so there's challenges with that are technical, but as the control algorithms get better for drones, and we have colleagues here at Western that are working on those things, we're optimistic that we can use those to capture great data in the immediate aftermath, particularly of the swaths, and connecting to the hailstone sizes as well with enough resolution.
Thanks. And we have no other questions from attendees, so I'm going to throw in the ones that I wrote, one or two that I wrote down. Gentlemen, you showed maps of, colored maps of storm swaths. And, some of them talk qualitatively about hazard. I'm curious, if you're in the worst, if I had a bunch of houses in the warmest spots on those maps, do I simply have a high chance of my house getting hit? Or is it that, everywhere in that warmest swath, hail is falling? I just want to understand a little bit better what those maps mean.
That's something that we suspected going into this. And perhaps now I'm a little more wary of looking at those hail swath maps. And I think I was picturing the latter point prior to the summer. If it's a red bullseye, it's maybe not uniformly, but through most of that area, you have large hail falling, or at least potential for large hail. What we're finding after this summer is that it's much more nuanced than that. Hailstones drift, the mesh product is created using data above the melting level. And there's something called hydrometeor drift when the hailstones, they'll drift as they fall from that level down to the surface. Some colleagues in Australia have been working on this to try and improve these swath maps. So that's one consideration. The other consideration is the amount of hail. Mesh doesn't really give us a good indication on the amount of hailstones or the uniformity of hail falling in that area. But what we are finding is that if you're in that bullseye, the potential for damaging hail to be present at some locations is quite high.
Mm-hmm. So it doesn't tell us hit rate, duration, some of the nitty gritty details about what we want if we want going to do damage estimation.
No, I mean, for that, you ideally need a distrometer device. Everything's got its limitations. Distrometers are great because they'll give the exact start time. They'll calculate exactly how many hailstones hit the device, what their impact energy was. You can get all kinds of useful metrics, but the sampling surface of those is tiny. It's maybe 20 centimeters across. I mean, a hail pad 60 centimeters across, but still, it's not representative of a terribly big area. So what one has to do then is collect stones in the vicinity of those sensors and build a reliable empirical relationship that relates to hail size and damage in a larger, surrounding area. Because radar, we're not quite there yet in terms of being able to pull out those nuanced points.
Cool. I have one more question I'm going to ask you to offer any concluding remarks you care to. Damage estimation is going to depend on vector velocity downwards and sideways of the hail as it reaches the ground surface. How much can we currently quantify about that? Will the distrometer network tell us more? How is the Northern Hail Project going to improve that knowledge?
Do you have any?
I can't comment on the distrometers, and maybe Julian can, but I would say that one of the things we have planned is to develop devices to measure terminal speeds in the field. We're going to develop that by dropping hailstones from drones in the lab and develop the tools to do that. One of the things you'd like to do is be able to calculate it. So some wind tunnel work will be required, but we need to pull all those things together. But we want to validate all of those kind of models. And then by doing measurements in the field of actual terminal speeds, which means we need to know crosswind speeds at that. So there's a lot of different parts to getting at that.
Awesome. All right, so we have about 60 seconds left. Do you have any concluding remarks that you'd like to leave us with?
No, well, thanks for the invitation. And we're honored to be asked this early in the project as we're learning. You described Julian truly is a hail expert, as I think everyone saw. I'm a rookie at this. I'm feeling like the first tornado damage survey we did in 2005, and I remember being completely disoriented when we did that, and I feel a little bit that way now with the hail work. But I'm optimistic that in the long run, like with the tornadoes work and the Three Little Pigs project, we can have an impact and reduce damage from these events as we continue this work.
Awesome. Julian, any last words?
Not just to echo what Greg said. Thank you again for the opportunity. And it's a bit geeky, but it's a very exciting time for us to be doing hail research. You were talking about wind and hail. We have high speed photography now with the GoPro, shooting at 240 frames per second at in full HD. And we can use those kinds of tools to look at the angle the hail's falling at. We can have an ultrasonic anemometer or something like that nearby measuring the wind speed, and we can back out some of these unknowns, or we can constrain them, because we have such great tools available to us now that they didn't have 40 years ago. So it's an exciting time.
Awesome. Gentlemen, thank you so much for speaking with us. Thanks everybody for attending today. Watch for our alert about next month's Friday Forum. Thanks everybody. Bye-bye.
Thanks, Keith. Bye.